Okay, so here's another example for class 6 where we're going to take some strain gauges and try to, from that information, try to figure out what the loads that are being applied to the thing. I often ask a homework question that's a little bit more complicated than this, but this is starting to approach some of the complication. This comes from Johnston's 7th edition, is problem 7-150, where we have this axial load P that's being placed in there and a horizontal load Q that are being applied at the top of this beam. And it's got a rectangular cross section of it looks like 2 inches by 6 inches. You can see where the rosette is applied to the thing, and we were able to measure that rosette and get the strain equal to these values, these 3 values, and you can all see that they're all laid out here. And we know that the elastic modulus is 29 million psi, Poisson's ratio is 0.3, and we want to find what these loads are on here. Okay, so here we go. So first things first, we can just from observation here see that the x direction is aligned with number 1, right? So that's going to be negative 60 e to the minus 6. And the 3 is aligned with the y, so we know that we're going to have 200 e to the minus 6 right here. We can also, just by nature of this location and these loads, we can see that these are not going to tell us anything about bending stress, right? Because this isn't going to cause bending stress at that location, and this is actually the neutral axis, right? If we had a strain gauge right here or right here, that would help us with bending stress, but we don't. We have it right here, which is the neutral axis. So we might be like a little bit confused as how we're going to be able to get to our desired result. Maybe we take it on faith, or maybe we start thinking about it a little bit further and see that, you know, transverse shear might give us the thing that we want, right? If we could figure out what the shear stress is at this element right here, because this thing is passing in that direction and producing transverse shear. So that's like the thing that we would want to work through. So we want to find what that gamma is. And if we look through our notes, we did an example, or one of the very first examples you did of our transformation of the thing, showed that gamma xy, when you had a orientation of here as they're 90 and 45 from each other, ended up having a relationship. I think I moved it over there. Let's see. Let's write it down. Right. It was right here. Right, so we made this conclusion that when we had this strain gauge, that the gamma was 2 times epsilon 3 minus epsilon 1 minus epsilon 2. Well, that's the scenario that we're in right now. So we can go back and do the rederivation of the thing, but we already know that it's going to be 2 times epsilon 2 minus epsilon 1 minus epsilon 3, and that's going to be the thing that's equal to, I got to write out the work. I was looking at the solution manual, so that's just going to be 2 times my 240 e minus 6 minus my minus 60 e minus 6, and then minus my 200 e minus 6. Yes. So what we're left with here is 340. In fact, we could probably do that in our heads. 340 e minus 6. And these are inches per inches, if you will, or we could just say that they are strains, right? We could say that that's the amount of this would be 340 microstrains in this case, but they're already micro. They're just there. All right, so if we have strains, we need stress. So we take the formulas that we use for biaxial stress and strain. And I want to double check on something here because their equations look different than mine. So let me pause 1 second. No, they're the same. Okay, so I was just went into a little panic right there, but don't panic. I was wearing that shirt in the last video, so maybe I should wear it again. We have x plus mu y, right? I believe those are the equations that I previously gave you. So we have for the E is 29E6 divided by 1 minus 0.3 squared. And then we had here for x, we have a minus 60 E minus 6. And by the way, we probably could have just said that the E's, the E6 and the E minus 6 cancel each other out. That would have been a little lazy though, right? Let me put a little parentheses around here. 0.3 and times our E to the Y, which was 200. E minus 6, right? Something we might note right in here, that right there, 0.3 times 200 is going to be 60. Minus 60 and plus 60 is going to be 0. Wait a minute. What happened? Well, look at this. There shouldn't be any normal stress in the x direction. Like, what would cause normal stress in the x direction? There's nothing. The only way there actually in this kind of sort of arrangement that you could have stress in the x direction is if it was hollow and has a pressure vessel, right? Remember that's to have biaxial stress, pressure vessel is about the only situation we've seen so far that we could actually have in two directions. It's really only going to have stress in this y direction, either by way of axial forces or from bending forces onto there. So we expect to get 0. If we didn't get 0, there'd be something wrong with our strain gauge. So here we go in the other direction. I just thought it was good to make that point clear by picking it apart and putting the numbers in. So now we got 29E6 divided by 1 minus 0.3 squared. And so now in the y direction, we get 200E minus 6, right? And then plus 0.3, but that's going to be times our negative 60 E minus 6 right in there. And so we get the stress in the y direction is, I don't trust their numbers, so I'm going to plug this into my handy dandy Hewlett calculator, which is the best calculator type there is. You don't believe me, but I think it's true. And so we have 200E6 minus, we have 60E minus 6, enter 0.3 times, subtract it out, and multiply it, and I get 5,800. That's what they got. 5,800 PSI, pounds per square inch. Cool. And then we already measured this guy right here. So if we want to get tau xy, well, first, okay, so I needed to do something first. We get g gamma xy, and we know that, I'll write it up here, that g is equal to E divided by 2, 1 plus nu, or 29E6 divided by 2, 1 plus 0.3. And so we get 11.1 yeah, I think so, E6, right? PSI, or 11.15 million PSI, right? MPSI, if you want, capital MPSI, if you want. So anyway, we stick this in there and get 11.15 E6 times our 340. I think I have there. 340 E minus 6, and what we're left with, I hope so, right? Seems like, no, I think we're okay. Yep. 29E6, 2 divided, 1.3 divided. Yeah, you get the same thing. Get 340E6 minus, and you multiply, and you get 3,792 PSI. All right, so that's nice. All right, so that's the stresses that we have at this point. But now our goal was to get the loads. Well, the only thing on here that's going to cause y direction stress is from axial, right? So the stress in the y direction is just going to be, they're calling it P, so it's P over A. So we could find what P is going to be if we get sigma y times area, and it's a rectangle. So we have our 5,800 pounds per square inch times a rectangle that is 6 inches by 2 inches, right? We could do that in our heads. That's 12 inches in 12 square inches, right? So 12, so we get 64, just double checking my answer, yeah, 69,600 pounds. That's what P is equal to. And now if we want to find out what, and I'm going to do this in a different way than they did in the solution manual, because they used everyone's least favorite thing, shear flow. But in a rectangle, like in this situation, and that's the force that's passing along to the side of this thing, right? That's going to be tau trans is going to be 3/2 V over A. In this case, they're calling it Q right there. So what I would say here is V, which is equal to Q, according to them, or QX, I guess they said. They called it QX, is going to be 2/3 tau times 2/3 tau times the cross-sectional area, which is going to be equal to 2/3 tau is 3,792, and the area was 12, and so what we end up getting, we get 30,336 pounds right there. So these strain gauges help to establish what the forces are on the thing. You can use strain gauges to measure forces in this manner. You just have to go through this manipulation of trying to come up with the correct words. Manipulation of the turning it into stress, and then finding out what the forces are by way of this relationship. Another force block, that's often what we'll call something. Some of my experience that I've had is with on a towing tank at the Coast Guard Academy, and they actually created a force block that looks similar to this. It's kind of it's only about the size, like this, about that big right there, can fit into your hand, and it was actually this kind of a cube-looking thing, sort of like this, and they had these so it had these like little posts, like that right there, right? So they're thin, right? So they look like that. I'm trying to draw them both in there. Here's another post, and it's coming up, and this has a very thin cross section right there, right? So each of these cross sections right there and right here, and there's another one back in the back. They're fairly thin, right? Thin rectangles, like have a cross section that look like that right there. And there was a piece that was stick downwards through here, and he was also kind of a rectangle and had a hole in it. And there was another piece right here, and it had so through there from the side, looking at the thing. Oops. Like that right there. Okay, so it had this post that's down there that's got a hole in it, and then there was another post over here, and it had like a I'm drawing the thing wrong. It had like a thing that's out through there, and there would be like a coil in there, and they'd be able to measure the distance that this thing moved. So what we was actually doing is sort of doing the displacement that was due to the amount of force. So this one would be connected to the top, and this would be connected to the bottom, and so like from an extension onto this would be like a little boat, right? That's in the towing tank. Of course, this thing is much bigger. This is just a little component that's inside there. But this would be the thing that's moving the boat along. So the resistance of the water would be measured by way of how these little guys bent and the distance that they would be able to measure through there. They were able to calibrate this up, and that's would be called a force block. And I wonder if I did a Google search on force block, if I'd be able to get some results that would describe that. But it's another way of measuring force. So force is actually a really important thing to measure, and we do it with strain gauges often, but there's other methods of doing it. Let me see if I could find it real quick. Well, anyway, I couldn't find a picture of the thing I'm describing, but it did refresh my memory that instead of a force block, that's often called a load cell. And there's often different kinds of load cells available using different, a lot of times the strain gauges will be inherent in them, but they may operate on other principles. But I just wanted to bring up this idea that measuring the loads on things are an important but challenging aspect of being an engineer. And that's one of the reasons why I brought up this topic, because I know that it might seem like out of place, considering that we just did pressure vessels and we were doing three-dimensional stresses, but now we have three-dimensional strains, and it brings into one of the very most important things I want to emphasize when trying to do an analysis, either to design or to analyze. Trying to find the forces that are applied to a structure or a piece of machinery is one of the most challenging aspects, and a source of a lot of uncertainty when trying to be a practicing engineer. So that's one of the reasons why I brought up this topic, because strain gauges are one of the main ways that we engineers, one of our tools to find loads. But it isn't a direct thing, right? It isn't something that we can measure directly. We have to kind of observe it and get from, kind of like find the implication of it. I'm trying to think of referential, maybe? Yeah, something like that. So anyway, I hope this was helpful, and we'll hope this helps with the homework when it gets assigned.